So I'll be talking about what privacy means in the context of machine learning. And I'll try to give you some insight about why privacy, when it comes to the case of machine learning models and systems, is a bit more delicate and subtle than the other types of systems where we are concerned about data privacy. Of course, you know that machine learning models have found their way into many systems in the internet. They make life easier. You don't need to understand the math behind it. You apply it, you get the classification that you need, and that's why they are very popular. Okay, and because of this application that they have, they are also been provided as a service by cloud service providers such as Google, Amazon, Microsoft, and others. And they work in the following way. They give you some basic API. You upload your data to the cloud, and then they train a model for you. You specify the classification task. They train a model for you. They give you some API, prediction API, to actually call the model and ask for predictions, right? And then you can use this prediction API on your system, in your app, whatever, where your users can benefit from this technology. So this is great. Makes actually brings machine learning to the masses. Many of us or many app developers want to benefit from this technology, but they don't understand the details. They don't want to follow with the best optimization techniques for machine learning and so on and so forth. They just can use this as a black box. Okay? This is a very good example of using machine learning models as a black box, and I use this as the case study throughout my talk. It is black box because when you actually send these prediction queries to the model, you don't know what the model is, you don't know about the parameters of the model, you don't see the intermediate computations that are done in the cloud. You just send an input, you get the results here. For example, you get the probability that this image belongs to any class, and here I show the probabilities in an abstract form as the length of these bars. Okay, so it's a probability that it's an airplane or a car and so on and so forth. This is great, but when we see this, we ask the following question of whether these machine learning models are privacy preserving. When you hear the term privacy, another relevant related security term that should pop up in your mind is the notion of trust. Okay, with respect to whom? In what trust model? Right. A very basic privacy issue, specifically about machine learning as a service, is that, well, you have to trust the service provider to give him the data, right? So he has access to your data. But that's not the privacy issue that I want to talk about. Okay, I'm going to talk about something more subtle. The question that we ask is whether, when you're using the machine learning model, you can infer some information about the training data, whether there is some information leakage through this indirect channel. Note that at the time that you're using the model for prediction, for inference, the data is gone, right? So the first data is used to train a model, then the data is gone, then you interact with the model, right? So then we want to know whether there is this indirect channel of information from the training data to the through the basically classifications. There is a canonical term here, leakage. So what do we mean by leakage? There are a lot of information that is provided by the classifier, right? It classifies dogs versus cats. This is some information that is leaked through the training data, right? It's without that training data, we couldn't do this classification. But what type of leakage is a privacy-sensitive kind of leakage? The information that we can learn about the data that we could not have learned if we didn't have access to this model. Okay, we couldn't have learned it from some other models. We couldn't have learned it from some other data, right? The information about whether this image is an image of cat or dog, we could have learned it from some other data set, some other model that was trained on similar data, right? But whether like this particular image was part of the training data, that's we could not learn from some other data set. Okay? So this is what I want to talk about. A very specific privacy issue, a fundamental canonical privacy issue with respect to any sort of analysis on a data set is called membership inference. The question that the attacker asks in this scenario is whether by having access to the output, you can tell whether a particular record was part of the input data set. Okay? In this case, whether a particular record was part of the training set of the machine learning model. I'll come back to this many times, why this is a relevant and sensitive type of question. Why does it matter? Basically, imagine that you can do this kind of membership inference attack on a model. What this means in the first place is that you could learn some very specific information about this data set, which is specific to this data set. Membership of a record in a machine learning set, training set, is specific to that data set. Okay, so it falls into the category of the sensitive leakage that I talked about. Okay, so it's a measure of how much sensitive information about your training data is leaked, the accuracy of the membership inference attack. These membership inference attacks could also be used as a stepping stone for more advanced attacks. Okay. So if I know how to do membership inference, having a full data record, I can tell whether this was part of the training set or not. I can use this to do a variety of inference attacks. For example, I can do reconstruction attack. I know some of the features of your record. I don't know the other ones. I can use membership inference attack to build the missing features. Okay. Sometimes this, in practice, sometimes even the knowing that somebody's record was part of the training set is sensitive. Imagine that, for example, that this data set was trained on the medical records of patients who had cancer, right? So as soon as I know that your record was part of that training set, I can immediately infer that you had cancer. Okay? So this could lead to some other kind of sensitive information leakage. And this is not unique to machine learning models. This has been studied for other types of analytics, for example, releasing summary statistics. You have a data set, you just compute some statistics on different features, the attributes of the data set, you release that, and researchers have shown that basically by looking at these summary statistics, analyzing them, you can actually run these membership inference attacks. But here is the details for the kind of, for example, sensitive for the kind of summary statistics. You have some underlying distribution of data. Some data set was sampled from it. This is the sensitive data set that you have. You compute some summary statistics on it. You release that statistics. Okay. There is an attacker who has a target record, wants to know whether this record was part of the set. What he can do is to just sample some so-called reference data from the underlying distribution, assuming that he knows the underlying distribution, who has access to some data similar to the sensitive data, can compute the same kind of statistics on that and run some statistical test of whether your record is more similar to the reference statistics or the published statistics, right? And then this can tell the attacker whether actually what is the probability that your record was part of this as opposed to the reference data. Okay, so this is the attack that has been covered in the literature. In the case of machine learning models, this is running similar inference attacks is much more challenging. Actually, especially in the case of black box access to the models. You don't know the model. You don't have access to the model. You don't know the parameters of the model. What you have is actually just some predictions on the queries that you provide. Okay, so you have indirect access to the model. And in some cases, you might not even know what data or what was the distribution of data that was used for training the model. So how can we go about and exploit the model's predictions given such limited access that we have to the model? The key insight to the attack that I'm going to present is that machine learning models tend to behave differently with respect to their training data compared to the data that they haven't seen, right? We all know that machine learning models overfit to their training data to some extent, right? And there's all this research in machine learning on how to train a model, to generalize it, to overcome overfitting, to have the same kind of accuracy on the training versus the test data, right? And this is actually what we are going to exploit to attack a model and infer membership of a record to its training data. Imagine that you have some data from the training set of a model. You can just provide that as an input, get predictions on that, right? Imagine that you have some input outside the training set of the model. You can get predictions on them as well. All you need to do is to find a way to recognize the difference between these two, the predictions that come from the training data and the predictions that come from the data outside the training set. And I've heard there's this technology that is very popular and useful, and people are using it everywhere. It's called machine learning, and we are going to use that to do this separation for us. Okay, this is a basic binary classification task. Okay, what we need to do is just say we have some samples from the predictions on the training data, some samples on predictions outside the training data. We train a machine learning model on it to tell us for a given prediction whether it comes from this camp or the other camp. Okay, so this is what the attacker can essentially do to build his distinguisher, to build his inference attack. So this would work only if you have predictions that are generated from your training data, only if you have predictions that are generated outside your training data. The attacker does not know which records are in the training set. So how can he, like, in the first place, create that data to build the training set for his attack model? Okay. So the idea to overcome this is that, well, maybe the attacker does not have the predictions on the exact records that were part of the training data or the exact record that were outside. What he wants to learn is the difference in the behavior of the model. Okay? And maybe he can learn this from some other models that have the same behavior. Right? And this is what we call the basically shadow training. We have some models, we train some models for the same classification tasks on data that is coming from the same distribution of the data that was used for training the target model. I'll come back to this of how we get this data. Then these models are trained for the same classification task, the same model architecture, the same underlying distribution of the data. They're going to have similar behavior, okay, in treating their training versus test data. Okay, so what the attacker can do is to train many shadow models on different data sets, okay, and then just query, because it was trained by the attacker, he knows the training and the test data for them, query the models with their own respective training and test data, get the predictions, and then use this data, which is labeled as member, non-member, in, out, to train its attack model. Okay? Is this clear? Yeah. So then the question is, well, I want to attack a model. I need to build a shadow model on similar data on the same architecture for the same classification task. The classification task is known. Okay, I'm attacking a model. I know what classification it does. I know the format of the input, the format of the output of the model. How can we get the architecture of the model? Right. So I'm training a model. The target is training a model on Google. Google does not tell anyone what the architecture of their model is. Okay, what model they're training. So in that case, then this is the trick that the attacker can use. Well, the attacker can also pay Google to train a model for it, right? If the classification task that I'm asking Google is the same as the targets, if the data that I provide to Google is similar to the data that was provided to train the target model, then there's no reason why Google trains a completely different model architecture for me than the other one, right? And I'm not sure if there are so many different architectures that Google use. Maybe they're adaptively choose some architecture. So that could be overcome that way. But if you want to, evaluate privacy of the model that you are training yourself, so then you also know the exact architecture. Okay. Then the second question is, basically some of these challenges are challenges if you want to really run this attack as an attacker. If you want to evaluate your own model, of course you know the distribution of your data, the model, and everything. But if you want to really attack an existing system out there, then these are obstacles. So how can you then get the data that is similar to the data that was used for training the model, right? Somebody is building a mobile app, just collected some data from its own users, sent it to Google, build a model, right? So how can you get the similar data, right? If you know the type of the data, of course you can go and collect it, right? So you know that it was some genomic data that was used to train a model, you can go and collect some genomic data. But in general, you might not know that. So what we suggest is to do some data synthesis. The goal is to synthesize data that is similar in distribution to the data that was used for training the target model. And if you want to synthesize data, you need a score function. You need a model that proposes something, some sample, and a score function that tells you if this is a good one or not. Okay. So how can we get this score function? Let's say I can generate some random inputs. I want to know whether this is similar in distribution to the data that was used to train the target model or not. I can get this score function from the target model itself. The target model does classification for me, right? If the target model has high confidence in classifying a sample, it means that the model thinks it has seen similar samples, right? Similar to the one that I'm proposing. So if the model is clueless, gives me some high entropy predictions, means that this for sure does not belong to the same distribution as the distribution of the input data set. But if it has high confidence, with 99%, he thinks that this is a dog, then it has some features there that to the model are similar to the dog. So what we do is that we just, in this large space of the inputs, we just need to run a search algorithm that walks in this space and moves towards the areas where the model has higher confidence on predicting the inputs. Okay? And then when we reach that space, we can sample from those points. Okay? This in general is not a trivial problem, but for some settings maybe you can do this. Okay? So this is a separate issue. But you can do this. So this is the overall architecture now. There is a model It gives us some prediction API. I can use the model to generate some synthetic data. I can use the synthetic data to train some shadow models. And then I can query the shadow models with their own training and test data and generate data as like, what are the predictions coming from members, what are the predictions coming from non-members, and then train my attack model. Okay. So then the attack model is just a binary classifier and gets a prediction vector and then gives me the probability that this comes from members or non-members. And then when I want to do the attack, I have one single record. I query the model, get the classification vector, feed it into the attack, and then it gives me the probability of membership, right? So in the case that, for example, you know some real data that's coming from the distribution of the training data of the target model, basically the number of queries that you need to send to get probability of membership is just one query. Okay, because you can train all your shadow models on the data and then build the attack model and just send one query to the machine learning as a service platform, and using the prediction vector you can do the membership inference. But if you want to do the data synthesis also on the target model, then you need to, prior to the attack, query the framework a lot. So we evaluated this on multiple platforms, including deep neural networks that we trained locally, some other machine learning models, in addition to the machine learning as a service by Google and Amazon. Okay. So here I just show the results of running this attack on one data set on Google. Okay. So this was a purchase data set, was provided by, in one of these Kaggle competitions for classifying customers, right? In 100 classes here. What we did was to basically train the shadow models and everything as I described, and then we ran the attack. In this plot, you see the accuracy of the attack, the precision of the attack per class, okay? Because the precision of the attack for different classes is different. Because for some classes, the model's behavior with respect to train and test is way more different than the other classes, okay? So maybe the model overfits more for samples on one class and doesn't overfit on the samples from the other class and so on. So there's a distribution of the precision of the attack over different classes. And here you see the cumulative fraction of classes for which you get a membership inference attack precision, right? So what you can see is that, for example, if you just look at the membership inference, I don't know, 0.9, you'll see that only 10% of the classes had precision accuracy less than 0.1, which means that for 90% of the classes, the precision accuracy of the attack was more than 0.9. Okay, so it's like almost certainly we could tell for 90% of the classes, for 90% of samples coming from the classes, that whether this record is member or not. Okay, so overall, like 93% accuracy. You give me a random record, I tell you whether this is member or not with this accuracy. This is when you train the shadow models on real data. If you train the shadow models on the synthetic data that you generate using the algorithm that I mentioned, then of course there is like a quality gap between the data that you generate using this, the synthetic data generator and the real data. And this quality varies for different classes as well. Okay. Again, it depends on how much information the model knows about each class. Here, to be more realistic, we did not use a balanced training set, okay? Because in practice, like the number of samples that you have per class might be different, right? So this is what we did for the target class, and actually that causes this quality difference of the synthetic data. For some classes, the model does not have enough information. The synthetic data that we generate for that class is of not good quality. Whereas for some others, the model has more information, can help us to generate useful synthetic data. That's why you see that there is this gap between the performance of the attack when we have the synthetic data or the real data. What I want to reiterate here is that we did all this without knowing the training algorithm, without knowing the type of the model that was trained, without knowing the parameters, without knowing the intermediate computations that was done, with nothing. Okay. So we cannot control how Google trains the model, but we thought about some simple mitigation techniques, and we evaluated what would happen if, for example, if you limit the number of predictions that you give to maybe, I don't know, top K, right? Top 3 predictions. Okay, this is a 100 class classifier. You only give the probability of on top K3, for example, classes. The accuracy overall was like 92%, and we'll see that even if you reduce the number of classes to top K, still the accuracy is large, which means that basically that overfitting is leaking a lot of information, right? So the accuracy that you have on the most probable class. And even if you just remove the information about like what is the probability, okay, or the confidence on the top class, still it leaks information, right? Even if I just say this is an image of a dog, without telling you what is the probability that it's a dog, just cat, something. Still the attacker with 66% accuracy can tell whether this was member or non-member. Can you guess why? How? What is there that the attacker can exploit? The attacker exploits the mistakes that the model makes. This is a picture of a dog. It's classified as cat or as, I don't know, fox or something else. The mistakes that you make leaks information. Okay, and this is what the attacker exploits. So let me step back and talk about the big picture here. There are 2 objectives. There is the objective of privacy that we want from a model, the objective of learning. And here I limit all this discussion to the case where we are dealing with black box access to the models. Okay, privacy with respect to information leakage through predictions. Okay, if you give me the model with all the parameters and everything, it's a different story, right? This discussion does not 100% apply there. So we have a universe of data. We sample a subset of that data for the training. We train a model on that. And the objective of privacy is whether the model leaks information about its training data, right, through its predictions. The objective of learning is whether the model generalizes to data outside its training set. Okay? So what do you think about these 2? These are different objectives, but very consistent with each other. In fact, overfitting is the common enemy of the 2. If a model is overfitted, it is very dependent on its training data, so it leaks a lot of information. Bad for privacy. It is very dependent on its training data, so it does not generalize to data outside its training set. It's bad for learning. So we, again, like a simple evaluation could help us to better understand this. You know that to overcome overfitting, there are many regularization techniques that are developed in the ML community. So we implemented a machine learning model ourselves, and then we actually added this regularizer term. this L2 norm penalty that you add to the loss function. And we see that if you regularize the model, there is a point where the privacy is increased, the generalizability is increased as well. Okay, you see here like that the attack total accuracy from 92% goes down to 77% after the model is regularized. The test accuracy of the model from 66% goes up to 72%. Okay, of course, if you over regularize, then you lose the accuracy on the model, but privacy always increases. Okay, because you just close the gap between the behavior of the model with respect to train and test. Again, this is not a provable guarantee that if you do this, the model does not leak information, but it shows the trend, it shows the connection between the two. Okay. Again, I emphasize this is for the cases where we deal with privacy and information leakage through the predictions. A model could generalize very well, but if you give me the parameters, I can reconstruct a lot of information about its training data. It's a different problem. So what this means is that maybe for the first time in the history of data privacy, this utility and privacy are not like in direct conflict with each other. We can construct some models that generalize well, which means that the utility is good, but at the same time, they have good privacy. Okay? We don't need to largely sacrifice one for the other one. Because usually privacy is achieved through some information hiding and randomization. And that might be detrimental to the utility. Here, this means that there is some way that you can achieve both. There are some attempts for this. And there are some good examples in the literature, very few, on how you can, for example, maybe modify the regularizer of the model to get privacy and utility at the same time. Okay, so I'd like to stop here, and if you have questions and you want to discuss something, yeah, please go ahead. Yeah. Go ahead.
See, one of the things comes to one's mind is in the language-based security, if you have a non-terminating program, and then you are not supposed to give back what is the situation in which you are stuck, because giving that leakage that you are not satisfied itself will give you some leakage kind of a thing. In the same sense, here also, the same thing is happening kind of a framework here. In the language-based security, technically, there is no real satisfiable solution for non-terminating programs, exceptions, and things like that, which is actually, you have shown in some sense, that's what is happening. That is one question. Do you have any comments on that?
No. So basically, anything that goes away from regular patterns leaks information. Okay, and that is what applies to that case that you mentioned. It applies to this as well, right? So if you have like a perfect, I mean, here also, like we are looking for like a perfect generalizable model that doesn't exist, right? Maybe for some particular tasks, yeah, if you want to train a model that does XOR for you, you can have a generalizable model, right? But for this like complex high-dimensional space data, we are not there. To the extent that we are away from that perfect, then there is some information that about the training data that is there, and then it could be misused. Yeah.
The question is, for example, Yahoo says that you can use it only for the purpose for which this data is given. So now, if that one has to be translated in training, that means that Google or whoever is training can be used only for the purpose of the training and nothing else for that. But in the machine learning, linking also comes together along with the policy. So in this context, it looks like very difficult to predict what is the policy the user should have, and it's also heightening to see Europe has something like a forget button. I have no idea if you say these things, how one can specify. Do you think you'll have to give a policy, and then with respect to which you can say whether the training or the Google is doing a problem?
No, I think it's very difficult to come up with those. But in general, like the simplest scenarios where you want to have some access control, right? So it's okay, you have access to this, you don't have access to that data, right? So if you're dealing with data, you can control the access, right? But when you're dealing with information, like you don't know, it's like this information leaks through all the computations that you do. So I mean, you can ask people, but whether like they can do this or not, it's like it's out of control, right? The model, you train a model, you have to build basically the defense mechanisms into the model so that the information about, for example, the records that were used during the training does not leak significantly, right? But like asking for not being used for other purposes is not possible. Yeah.
Hi. Excellent talk, Reza. I very nicely explained. I fully appreciate all these things that you're raising. Could you go back a couple of slides, because I've the one where you say you can sample in order to build your yeah, that one. So you actually did this, and you said you used the data set from Kaggle. Was it face images, or what kind of data?
No, it was like a purchase data set. You purchase this item or not, and like there are like thousands of items. So like a binary
like
feature.
buying.
Yeah. So you bought this or you didn't buy this. So it's a long binary vector.
Okay, so it's not like face images.
No, it was not face images.
Okay. And how did you synthesize then?
So it was like a simple hill climbing algorithm. Right? So
Okay.
we start with some random sequence, and then we flip the bits. We move towards the direction where the basically the confidence of the model increases. But for faces and so on, I guess like you need some model that proposes something that comes from some distribution similar to the faces. Maybe then you can have a score on that.
That leads to my second thing. So I've been working on face recognition for a long time, and I do have a very good way to synthesize realistic faces. Can you use that to build a better attack model, number one? Number two, move your curve so that you're on the high, your final curve. So that, in other words, if I give you a tool that can, at least for faces, if I give you a good face synthesizer, can you move that utility privacy curve higher?
So basically, if you give me something that can generate a better quality data, okay, it increases the, basically, let me show you here. It decreases the gap between the accuracy of the attack when I have the real data and the synthetic data. If my synthetic data is not of good quality, then actually I'm not exploiting all the information that is leaked through the model, okay? Because then the behavior of my shadow models would be different from the behavior of my target model, right? So if I have a good
synthesizer
generator, then I can exploit this information to the extent that is leaked.
Okay. But on the flip side, can my generator help you improve that final curve?
Your generator help, not in this framework, not in this framework. Maybe in using some other techniques.
Okay.
But not in this framework, because this is only maybe if it's used, for example, in some way as a, I don't know, use it to data augmentation, increase the generalizability of the model and so on. Maybe that could be helpful there. But
despite all the maybes, one thing is for sure, I need to talk to you more. So
sure.
thank you.
Hello, can you
Yeah.
go back to the mitigation slide?
Which one?
Mitigation, the last mitigation. I think the last two, maybe last two slides.
Last two.
Yes. This.
This one?
The previous. Mitigation. Yeah.
Mitigation.
Yeah. Here, you have the other slide. I guess mentioned with the mitigation, the the attack accuracy is decreasing, but the leakage also, privacy leakage get better. That's right. Yeah.
This one.
Yes. So can you talk about a little bit how do you do the mitigation? What did you do to the mitigation?
So this is a regularization. Basically, we just did a simple regularization. Basically, the idea behind this regularizer is that it penalizes the parameters of the model if they're large. Okay? It prevents the model parameters to grow arbitrarily large to fit the training data. Just smashes them.
Oh, so you mean just like control the data set?
No, the parameters of the model.
Parameters. Okay. Yeah. Thank you.
Yeah, sure.
Maybe one last question. Thank you.
Have you considered looking at the bottleneck principle, the information bottleneck principle? Because the idea is that you want to basically minimize the mutual information between the input and the intermediate compressed random variable, at the same time maximizing the mutual information between that random variable and the label. And this seems, to me, one of the issues with this is that when you train, oftentimes the issue also lies with the cost function, that you basically just use off-the-shelf cross entropy. And when you actually train with the information bottleneck, my hunch is that I'd be rather, I'm actually a little bit skeptical about at least this level of efficacy kind of being replicated. So have you actually tried this out?
So basically, a better way to reason about privacy is not through mutual information of the input and the output, right? It's a better way to look at it is through the notion of indistinguishability, right? What we want is that we want to make two states of the world, two different data sets that could have been the training data, almost indistinguishable from each other when we see the prediction, the output of the model. Okay? There is still information leakage, but the information leakage is not to the extent that can help you to identify what exactly was the training data, right? Because this is like a huge set. You get the training data from here. You could have get it from here, right? If my data is from this part of the distribution, your data is from this part of the population distribution. Of course, their predictions and so on are a bit different. You should be able to tell whether I'm from this side or from the other side, right? The thing that you should not, the information that should not be leaked is whether these two overlapping sets, whether this one was the training data or this one, right? So when you get closer to the secret, you should not be able to identify exact secret, okay? So in case of a training set, so if you have two data sets that overlap a lot except few records or so on, you should not be able to tell whether the training set is this one or the other one, okay?
Right.
So indistinguishability,
that,
yeah.
My hunch is that it's got to do with when you say the model is learned. Part of the sinister aspect emanates from the fact that the cost function that you use is usually off-the-shelf cross-entropy like cost function, which inherently does encourage memorization. So my hunch is even if you were to if you replace the cost function that you use when you basically fit the model, I think that'll bring about a fair bit of improvement. That's more.
Yeah, it is true. I mean, the cost functions that you use, even for example, in the case of deep neural networks, the activation functions that we use and so on, the architecture of the model, they all contribute to how much information is memorized, okay? But at the end, when you want to evaluate what privacy is, the better way to look at it is through indistinguishability rather than mutual information.